Hi, my name is Alexander Lout, and I will be presenting the following topic titled Influence of Transverse Motion on Longitudinal Space Charge in the PS. This work was conducted in collaboration with my supervisor Alexandre Lachine within the Beam and RF Studies section at CERN. One of the key motivations for studying space charge effects in the PS is to address longitudinal beam instabilities below or about transition crossing. Ultimately, to provide high luminosity to the LHC, longitudinal stability must be preserved to ensure efficient coupling between injectors. Particle bunches passing through perturbations and discontinuities in the beam will generate weak fields that will induce a longitudinal voltage kick along the beam. These perturbations can be represented and tallied as linear reactive impedance sources, and conveniently, intensity effects of the bunch's own self fields can similarly be represented as a compensating space charge impedance. In both cases, local fluctuations in charge density near the head of the bunch can induce further destabilizing perturbations towards the tails, leading to beam breakup. Breakup can be avoided by correctly modifying the RF phase jump about transition. Additionally, the effects of space charge can be validated in an experiment by means of bunch length oscillations after having artificially reduced the predicted simulation effects by 30%. Accordingly, identifying this discrepancy is of key interest. The RF manipulations in the PS are rather dynamic, first accelerating the 8 bunches injected from the PS booster to high energies where space charge can be neglected. Then the bunches are merged, accelerated, and then split to match the admittance parameters of the SPS. This dynamic process of the PS's batch compression, matching, and splitting is of key importance in maintaining transmission efficiency between injectors. The motion of particles within a synchrotron's ring can be primarily decomposed into kick and drift steps, effectively evolved discretely once per turn. The resulting equations of motion solve for elliptical trajectories in longitudinal phase space where oscillation amplitudes are minimal and the effective RF voltage remains linear. The angular frequency of these trajectories can be described as the synchrotron frequency. The synchrotron frequency is reduced by the non-linearity of the RF gradient for particles with larger oscillation amplitudes. This synchrotron frequency spread, or tune spread, induces a filamentation of the bunch, which can be seen to dampen phase space oscillations, eventually reaching a stable equilibrium. As described previously, discontinuities in the beam pipe will induce wake fields whose longitudinal effects can be characterized by a linear reactive impedance. The equivalent space charge impedance can be shown to scale with a geometrical factor G, dependent on the relative transverse position R within a bunch with respect to the beam radius A and aperture radius E. The space charge impedance scales inversely with beta gamma squared, and so accordingly, longitudinal space charge is a largely non-relativistic effect except where the total intensity is extremely high. The relative space charge effects for off-axis particles can be described for uniform, parabolic, and Gaussian transverse bunch distributions. However, the effect of making these distinctions is minimal, and so the numerically cheapest model can be used. Historically, longitudinal trackers like Blonde implement space charge effects by homogeneously assuming particles occupy the same position in transverse phase space, an approximation in need of validation. The PS optics are largely periodic and can be easily incorporated into a longitudinal tracker where bivariate transverse bunch distribution can be tracked with respect to the PS aperture, evaluating the total incurred longitudinal space charge felt by a single particle for a single turn along the ring. Basic scaling laws can be derived to describe how this ring averaged effective geometry factor scales with particle dispersion squared, sinusoidally with transverse phase advance, and mostly linearly with transverse admittance. However, the domain is limited by high dispersion particles where collisions with the aperture is inevitable. Accordingly, a response matrix can be developed to effectively characterize a particle's felt longitudinal space charge along a ring without the need for additional transverse tracking. This effective geometry factor was implemented in the longitudinal tracker Blonde, where the geometry factor induced a variance in the nominal synchrotron frequency spread. The observed blurring is strongest towards the center of the bunch, where the accelerating gradient and maximum dispersion is highest. On the right in blue, we observe tune spread of traditional single particle motion without intensity effects. In orange, intensity effects are added by homogeneously applying a space charge geometry factor. And in green, we include transverse motion by incorporating the described effective geometry factor. We see an increased filamentation rate which would provide similar longitudinal stabilizing benefits as synchrotron frequency spread for single particle motion. Thank you for your time, and please feel free to contact me if you have any questions or suggestions.